Fine, so we're going into topic 4, the question 12. So I've got my topic 4 equations from the data booklet there. So 12, the shock absorbers of a car in good working condition ensure that the vertical oscillations of the car are, and this is critically damped. You don't want when you're driving over a bump in a car that you have undamped or lightly damped, even moderately damped, because um, you want the amplitude to decrease as quickly as possible back to your equilibrium position. So you want that to go down fast, and that occurs when you're at critically damped. Good. Going into here, 13. The graph shows how the acceleration A of 4 different particles varies with their displacement x. Which of the particles is executing simple harmonic motion? So the defining equation for simple harmonic motion is minus omega squared x, where omega is the angular frequency. So you can see that as far as a and x, that a is proportional to x, and there's this negative sign showing that it always operates in the opposite direction. Your acceleration is always towards the equilibrium. So B would be the correct answer there. We need a proportion graph and we need a negative proportion like that. And going on to 14. Got this one over here. The diagram below is a snapshot of a wave of wavefronts of circular waves emitted by a point source S at the surface of the water. The source vibrates with a frequency of 10 Hertz. Now we've got to work out the speed. So our formula relating to that is V. V is equal to F times lambda. Now we have our frequency, which is 10. We need to find out what our lambda is. Now that would be from one wavefront to the next wavefront. And I think you can see if this is 1 centimeter from there to there, that this lambda is going to equal 1.5 centimeters. So you've got 15 meters per centimeters per second, because this is a centimeter. So answer should be C for 14. Fine, going down to this one over here. Two coherent point sources. This idea of coherent, it means that they're at the same frequency. Sources S1 and S2 emit spherical waves. So these lines over here are actually your wave fronts, and they actually correspond to your crests. And in between them, you've got your trough. So from crest to crest, and then you've got your trough in between. So looking at this, at point P, you see that you've got two crests meeting together. So you would expect that to be a maximum. So we would be looking at maximum and maximum. And here you can see that for the one wave you've got a crest, and the other it's in between. So you would expect destructive interference to be taking place there. So it would be a minimum. So it would be A would be the correct answer here. Now we are moving on to 16, and here we are going into our unit 5. So let's just change our data booklet to there. We have got this, and we have got here. It says an alpha particle is accelerated through a potential difference of 10 keV. Its gain in kinetic energy is. Now, just remember, from your definition of for the potential difference, V is equal to the energy or the work per charge. So W is equal to V times Q, or the energy that it gains is equal to that. Now we have got 10 kV, so that is your V. is equal to 10 kV. Now, your charge here is, we are dealing with an alpha particle. Now, an alpha particle has actually got a 2 plus charge. It's 2 plus. So you've actually got 2 elementary charge, or the charge of 2 electrons, but they are positive, so the charge of 2 protons. So in actual fact, you've got 2, it would be actually 2e minus or 2e plus. That's the charge that you've got on it. So your EV that you have got would equal, it would actually equal to 20k EV that you would have, because you 10 kilovolt times the 2e that we have for the 2 elementary charge. So we're going to have D is the correct answer for 16. Here it says a copper wire of electrical resistance R has length L and cross-sectional area S. Another copper wire has length 2L and cross-sectional area S2. Which of the following is the resistance of this wire? Okay, so which formula are we looking for? Well, we're actually going to be using this, where we've got our resistance. This is the resistivity, or it's a measure of the resistance, and because it's copper, this would be the same for both. So here we're just looking at that and that. So if we've got, for this one over here, we've got R is equal to rho L over A. Now we have doubled the length, so in actual fact we've got we're going to make the resistance twice the amount, but the cross-sectional area is S over 2. So we've halved that, so it's this is being divided by 2. So we have actually made it thinner, and in actual fact that also increases the resistance by 2. So in actual fact this is going to equal to 4 rho L over A. We've actually going to have increased it 4 times. So your answer for 17 would be D. For 18, the circuit shows a light-dependent resistor in series with a resistor and a cell. The EMF of the cell is E, and the internal resistance of the cell is negligible. Now, these light-dependent resistors, basically what happens is that the resistance decreases when you have light shining on them. So this may have a certain resistance, say of 100 ohms, but when light is shone onto it, it may drop down to say 20 ohms. So that resistance will decrease. Now we want to find out what will be the potential difference across the resistor when light shines on it. So this resistance is actually going to decrease. Now the potential difference across here, V, would equal I times R from this formula over here. V is equal to I times R. Now the resistance should remain the same, but what about the current? Well, the current in the whole circuit is actually going to increase, because I is equal to V over R, and that's in the total circuit. So that would actually be your EMF there, the EMF of the cell, and the R total. And because this resistance over here has decreased, because that's gone down, this I is going to actually increase. So because that increases, the potential difference across this resistor, this I value will increase. That's going to increase, and therefore the potential difference across your resistor will increase. But it will increase, but always be less than E. You cannot have more energy being used up in a resistor than actually supplied by the cell, because this is the energy provider. This can only use up as much energy as provided. So it will increase, but always be less than equal to E. So C is your correct answer for that. Fine, going on to 19. We have the radius of a charged spherical conductor, because this conductor is R. Which of the following graphs best shows how the magnitude of the electric field strength E varies with distance R from the center of the sphere? So we're looking at from the center of the sphere. So you've got a sphere like this, but what happens with this is that all the charge actually goes onto the outside. So you'll have your charge, if we say it's plus, it will all go on the outside. All forms on the outside. It goes as far away from each other as possible. It's if it's a sphere like this, it will be all over it like that. It actually forms an electric field something like this. If I just bring in the formula, the formulas that you're going to be using for this is actually further down here. We're now moving into our topic 6 questions, and we get this. We get our F is equal to that for electric field, and we get this. And actually, we find that our E is proportional as far as 1 over R squared. It's going to decrease. So we're going to have this decreasing like that as a curve. So that would be your correct answer there, would be D. And then here, looking at 20, which of the following gives the acceleration of an electron of an electric charge E and mass m in a uniform electric field strength of E? Okay, so we need to look at this formula over here. And then think also, if we're dealing with acceleration is obviously F over m from Newton's second law, force is equal to mass times acceleration. Now F here is equal to F, if we look at F is equal to EQ. So if we put that into there, we're going to get EQ over our mass. And because we're dealing with an electron, our charge Q is actually E, so this will equal Fe over m. And so for question 20, the answer is C. Sorry, it's not F. It's the E over here, like that. So it's 20 there. Fine, going down here to this one. It says a particle of mass m and charge q moves with a velocity v perpendicular to a magnetic field. The magnitude of the magnetic field acting on the particle at a particular point is F. Of the magnetic force acting on the particle at a particular point is F. Which of the following gives the magnitude of the magnetic field strength? So, which formula are we going to use? Well, we've got this one over here. We've got a force, we've got our charge, we've got our velocity, and we've got our magnetic field strength. Because it's acting perpendicularly, that will be the sine of 90, which is 1. So we don't need to worry about that. So we've got our F is equal to QVB. So our magnetic field will actually equal to F over QV, like that.